All right. Well, hello, chemists. How are we? All right. And I see we have Alistair with us this afternoon. Well, Alistair, hello. Welcome to the masterclass. Well, hello, chemists. So let me get started here. All right then. So on this one then, chemists, here we go. Let me share my screen right here. Okay, let me adjust my video and connect there. All right. So on this one, chemists, first off, welcome. All right, number one. And second off, welcome to the masterclass if you're new joining us. All right. So what I do need you to do, though, Alistair, is if you do me a favor, could you hit the mic on your end? All right, you are on hot mic right now. Okay, which is okay. All right, but here we are then. All right. So on this one, chemists, this is where we are from last week. What I wanted to do this week is I wanted to cover balancing redox equations in alkaline media, number one, and then I wanted to do a couple of past paper questions. All right, the first one is going to be on just your standard redox reaction, typical past paper question. Then I wanted to look at one on a titration, a rather simple titration. And then if we got time at the end, I wanted to do a redox titration that you probably see in year 13. Okay, so see how much we can get done today. All right, but anyway, here we are. So on this one then, chemists, let me go move my video link and everything out to the page there. Okay, then, so get pen turned on. So this one then, I'll write down the rules that we did last time, okay? And so let me move this up to here. So I'm going to pick up exactly where we left off last time, and this is right here. This is balancing equations in royal blue. All right. All right, so balancing equations in alkaline media. Okay. In alkaline media like so. Now, the reason why, alkaline solution, the reason why I mentioned this one, chemist, is because once every 5 years, the exam board likes to put one of these questions on. As we all know, the questions, they do recycle once every 5 years. Okay, so I have seen alkaline equations beyond the exam number one. And number two, if you're doing in year 13, if you're doing fuel cells, for example, then you'll also see these in these alkaline equation type questions in fuel cells. All right. So here we are. Let me move this down a little bit here because we're going to go chalk this up. So start off with Kermit the Frog green. You know, it's my favorite color right here from bit paper. We love bit paper. All right, then. So what I'm going to do then is this. You take a look at this one. You go, well, yeah, like what are we going to do? Right. So look, you break it down into two half equations. All right. So now all I'm doing on this one is I'm just following along. All right, as in, see the ClO3 minus on the left. Well, I'm thinking what's going to happen? It's going to have something, it has to connect to something on the right-hand side. And so logically, I could see it connecting to ClO2. All right, oxygen, ClO2. And the Cl minus here, I can see this one connecting here to the Cl2. So just like we did with the acid solutions. All right, we do the same thing with the alkalis. There's only one extra step that you need to do. So having said that, let me go back to royal blue here. All right, I'm now going to break this apart. And actually what I'm going to do is I'm going to put in the oxidation states. Now we know that Cl2 is chlorine in the neutral state. Therefore, it's going to be neutral. It's how chlorine exists in nature right here. Now, obviously, chlorine is -1. So very first thing, just some housekeeping like this, okay? Let's put the oxidation states in. Now, on this one then, here, right, we said last time, we said, well, oxygen is -2. Why? Well, because it's an oxide. There's no way it's going to be a pure oxide like H2O2. Therefore, it's going to be -2. And so, oh, let's see, mental math. Something -6 is -1. Am I thinking this is +5? Okay, so chlorine +5 minus 3 times -2 up here, right? So I've got chlorine, wherever that is, all right, minus, well, I've got 3 times -2 is going to be -1. Therefore, I got chlorine as being +5 right here on a Sunday afternoon here, like this. I've got this done, this done, this done, this done. And over here, obviously, this is oxygen is going to be -2 again. And so I'm thinking that chlorine is going to be +4, right? I mean, you know, I always like doing these live because I like doing it from the student perspective. You know, it's not scripted. It's not like, oh, yes, I've memorized this. I've done the problem so many times. No, it's live. And so just like you're doing it on the actual exam, right? So here we are. Chlorine's going from +5 then down to +4. And so I'm going to put this, like we did last time, I'm going to split my screen like this. Oh, I do love bit paper. It's a lovely, lovely product, bit paper right here. So we said on this side, we're going to have the reduce section on this side, and we're going to have the oxidize section on this side. You know, like we talked about oil rig. All right, so oxidation reduction is just, you don't have to, but on the other hand, you're thinking, oh, it's a way of just keeping things organized, right? So anyway, I'm going to put that because this is reduced. I've got what? ClO3 minus like this is going to go down to ClO2. All right, it's going to be reduced. And on this side, I've got Cl minus, and that's going up to Cl2. All right, so all I've done, like I did last time, was just take the equation, break it down into 2 half reactions. Now, we said last time, and let me, just in case you forgot. All right, so we'll put the rules down here as well, right? Like this one, we said this one. Rules. So the very first thing we did is step 1. Can I put down determine oxidation state? No, I think I said last time I talked about variable oxidation states. Okay, why non-metal and transition metals have variable oxidation states. So number 1 is determine oxidation states, like so. Oxidation states, hold on. Like this. Okay, now the next thing I'm going to do then is I'm going to balance for the change in oxidation state by adding in electrons. And balance, can't seem to write and talk this afternoon, hold on. All right, balance a change in oxidation state. Okay, like so. Right then, so, well, this is -1, and this is 0. So, right, oxidation states. And then can I say, all right, you've got to balance for atoms as well. So I've got to be a little bit careful here when we do this one. All right, so if we've got Cl minus goes to Cl2, I'm going to put a 2 in front of the Cl's first, right? So I've got the atoms that change oxidation state balanced, all right? So Cl minus goes to Cl2. And so each chlorine is going from -1 up to 0. It's losing 1 electron. There's 2 chlorines. So therefore, I'm going to write this down as being 2 electrons. Yeah, like this. Okay. And on this side then, just a quick recap, this is +5, like so. And we said this is +4. All right. And so I'm thinking chlorine's balanced on this side, chlorine's balanced on this side. So therefore, I'm going to add 1 electron to the left-hand side, right? Now, of course, you're thinking, yeah, it would make sense if the electron is on the right-hand side of one half equation, it's got to be on the left-hand side of the other half equation, right? So like this. All right. Now, step 4 then is I need to balance for oxygens and hydrogens, right? So step 4 is balance for oxygen by adding water. Like so. And so I'm thinking, right, on this, on the left-hand side, the oxidation half reaction, you're thinking, yeah, I don't need to do anything else because this is, there aren't any oxygens or hydrogens. This is actually done. Or check mark right there. But on this side, right, on this side, what I've got to do is I'm thinking I need to balance out for oxygens, right? I'm going to add water to the right-hand side. Why? There's 3 oxygens on the left and 2 oxygens on the right. Like so. And of water, right? Now you're thinking, okay, done this bit. So let's do next bit then. Balance the oxygens by adding water, correct. Well, now what I need to do is I need to balance for hydrogens by adding hydrogen ions. Balance for hydrogens by adding hydrogen ions. Yes, no. Chemists, the way that I teach it, it is algorithmic. It's like step by step by step, okay? So I do realize that there are more than one way of balancing redox reactions in acidic and alkaline media, okay? I'm just doing it the way that makes sense, well, for me, and hopefully makes sense for you. But if you do pop out on the internet, there's loads of different ways, balancing them. Just pick one that works for you, okay? So anyway, I've got 2 hydrogens on the right-hand side here. So I need to add 2 hydrogens on the left-hand side of my arrow. So right here, then I've got 2H plus and 1 electron and Cl. What happened to my pen? Don't know. All right, hold on. I can write Cl better than that. Hold on. ClO3 minus goes to ClO2 and H2O. All right, then. So this one's balanced, right? Good. Now, the next step then, just like we did last week, right? So if you want to catch the live stream last week, then you can, obviously I do live stream these up to YouTube for easy student access, or if you want like the entire series, just, pop out to my website and they're all cataloged for you. I think easy access for students to gain the knowledge. Now, by the way, chemists, can I do it at the same time? Yes. I run these master classes every Sunday, and they are student driven, meaning that if it's something that you want me to cover next week, just send me an email and I will do that for you. Okay. All right, then. So now I'm going to take this reaction here, and I'm going to take this reaction here, and I'm going to balance them for electrons, and I'm going to add them together. Now, I always put the one half reaction that's been oxidized on the top. Why? I don't know. I can just, it's like I can see the electrons on the right-hand side, and I know the electrons on the right-hand side have to be given to whatever's on the bottom, because this is obviously oxidation. You know, we're losing electrons. And so down here, then it's going to be this. All right. ClO3 minus, arrow, right, ClO2 and H2O. And this is obviously going to be reduction because, you know, we talked about last week, right? We said if something gets reduced, it's got to be getting the electrons from somewhere. It's getting the electrons from whatever is oxidized. So to me, I can see the electrons on the right-hand side here, and they fall down to this equation down here in the bottom. Now, I've only got one electron up here. There's two electrons up here. So what I need to do is, let me change pen colors. Now, we'll use Syracuse orange. Yes, somebody told me this is actually Syracuse orange. I know it's something to do with the football team right back in the States there. All right, so I'm going to multiply this through by 2. Why? Well, logic would dictate that the electrons released during oxidation must equal the electrons gained during reduction. Otherwise, we're going to have a bit of a problem. Right, so let's say like this, like this, like this. Good, trying to get a straight line. All right, so here we are. So what I'm going to do is, to speed things up, I'm going to multiply through by 2 and add them together at the same time. All right, so here we are. So the top one then is just going to be 2Cl minus, like this. Left-hand side is 2Cl minus, and I'm going to add what's in the left-hand side down here, 2H plus 4H plus, like this. And then I've got my 2 electrons on the bottom left. I'm going to cancel out the 2 electrons at the top right. Not worried about this one. So we've got 2 chlorines, 2 hydrogens times 2 is 4 hydrogens, arrow. And then I've got Cl2 like this. My electrons cancel out, obviously, plus, hold on. Did I not? I did not. I made a mistake with an arrow somewhere, chemist. Hold on. I am, ding, 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 ding. That arrow should actually be a plus. All right. Like I said, chemist, I do these live. All right. So, you know, mistakes are thrown in for your amusement pleasure. Right, here we are. So 2 chlorines, 2 chlorines, 4 hydrogens, yes. And then I just need to add in the 2 ClO3 minus, like so. 2 ClO3 minus, like this. That's chlorine. All right, chlorine, hydrogen, chlorine, yes. Arrow, here we are. All right, Cl2. All right, and 2 ClO2, multiplying through by 2, and 2 waters. All right, so I show you the next step. Let's take a quick look. So 2 chlorines, and you've got the Cl2, and this is done for the first bit. So 2 hydrogens times 2, 4 hydrogens, 2 ClO3 minus, 2 ClO2, and 2 waters. Right. Now, this is where you would be if you were balancing in acidic media. Now, acidic solution would be done. All right. In alkaline, there's only one extra step, chemist, and it's so easy. All right, all my A-star students, don't worry about it, is this. Look, all you got to do is this, is that you just add the same number of hydroxide ions as hydrogen ions. Yeah. Now, the reason why you do this is because it's an alkaline. solution. Therefore, you can't have hydrogen ions floating around in alkaline solution. So if I've got 4 hydrogen ions on this side, I'm going to add 4 hydroxide ions on this side, like so, right? And I'm going to add the same number of hydroxide ions on the right-hand side. Now, you know, where's my Kermit the Frog? I love Kermit the Frog green like this, look. The hydrogen ion here and the hydroxide ion, yeah. Well, now you know this is just going to make water, right? I mean, yeah, come on, like this, right? And so here we are then. I'm now going to write it down as, back in royal blue, 2Cl minus, like this, plus 4 waters, plus 2ClO3 minus, arrow, right? Cl2 and 2ClO2 and 2H2O and 4OH minus, like this, right? Right. Now, next one down is I'm going to simplify down. Meaning, okay, and student asked me last week, they said, well, when you say simplify down, do you mean you've got to divide through by, you know, the least common denominator for all the numbers in front of the species? It's like, no, what I meant was, and questions are good, chemists, you know, I mean, if you have a questions, email me and say, can I explain this one? I say, yeah, sure. What I mean is this, look, the 2 waters on the right cancel out with 2 of the waters on the left. Not that you divide everything through by some coefficient and, you know, no. So here we are then, our final answer, and we'll do one more, all right, is this one. Look, it's 2Cl minus, like this, and 2H2O, okay, plus 2ClO3 minus goes to Cl2 and 2ClO2 and 4OH minus, like this. Right, done. Now, chemists, this one, I've seen this one floating around, no pun intended, floating around on the exam, like once every 5 years. And you also see it in year 13 when you're doing fuel cells. Like when you're doing fuel cells, you need to be able to do the fuel cell reaction in acidic media and in alkaline media. And they can expect you to balance it in alkaline media, the 2 half reactions that they give you. And, well, it's dead easy, right? Okay, good. So, I've only said that, chemists. This is the first one. All right, and so if we have any questions, pop them into the chat stream for me, okay? Got limited real estate here, so I've got my iPad out and everything else, you know, trying to make it work, okay? But any questions or comments, by all means, in the chat stream, either on the YouTube live or on Zoom. Let's do another one. Now, the reason why I picked this one is like, ooh, perfect cup of tea on this one, because this one's a bit tricky, right? I'm thinking, what? You know, I mean, it just looks alien, but let's have a look at this one. And so this one here, right? Again, what I'm going to do is I'm going to write the 2 half reactions. And so I'm only eyeballing, looking at the chromium 3+, and I'm thinking, well, the chromium 3+ must have something to do with the dichromate on this side. And the oxygen on the left-hand side, well, it's got no option but to be something on this. All right. You know, because when you look at it, you think, well, chromium 3+, it couldn't all of a sudden transmute itself into water. It's got to be with a chromium, right? So here we are then. Let me do this. All right. Yeah, and this is another example of balancing redox in alkaline solution, like so. And it's the same thing. The reason why I picked this one is, oh, it is a bit, well, funny looking, isn't it? So we are. So you've got O2, yeah, arrow goes to H2O. And then, well, they got chromium 3 plus is going to Cr2O7 2 minus like this, right? Okay, now then, look at this one. Let me change pen colors. Very first thing I do, just to keep things organized, we'll do it in pink, like neon pink, is I write the oxidation state down. Why? Well, because I like to have oxidation on the left and reduction on the right. So chromium 3 plus like this. And then on this one then, so let's say, well, all right, I've got 2 chromiums minus 2 times, hold on, that's supposed to be 7 times minus 2, all right, for the oxygen. Now, chemists, it's safe to say it's going to be -2, the oxidation state of oxygen. Why? Well, because it's not a peroxide like H2O2. All right, so anyway, this is going to be what, 2 chromiums minus 14 is -2. And so what, each chromium is going to be +6, all right? So finish this off real quick. 2 chromiums minus 14 is going to be -2. So yeah, each chromium is going to be +6. All right. Now, like I mentioned last time, right, chemists, there's certain oxidation states you just need to know, like common oxidation states. You know, we talked about oxidation states are variable for transition metals and for non-metals because it's got to do with the number of valence electrons they have outside the noble gas core. Number one, the fact that transition metals have D block valence electrons and non-metals are on the right-hand side of the table, and you're thinking really high electron negativity, low ionization energy, you know, like the arrows and everything else. But chromium +3, +6 are 2 common oxidation states of chromiums. There may be ones that you're thinking, yeah, maybe I should like write these down, okay? So anyway, this has obviously been oxidized. So this one is going to go up to here. So oxidation like this. And so I've got, yeah, chromium 3 plus arrow goes to Cr, that's a Cr, believe it or not, 207, 2 minus. Oh, let me do this one real quick. All right, so I've got 1 chromium here, 2 chromiums over there. So I need about 2 in front of the chromium, the element that changes oxidation state, right? Done that. Now, each chromium is losing 3 electrons. Now, because there's 2 chromiums, that would be 6 electrons, right? Yeah. Okay. Let's see. So now I've got to add in some water. I've got 7 oxygens on this side. So would it be, all right, 2 chromiums, 3 plus, and 7 H2O. Okay, goes to Cr2O7, 2 minus, and 6 electrons. Yes. 7 times 2 is 14 hydrogens on the left. So I need to add 14 hydrogens on the right. Yeah, and okay, look, do you see it's algorithmic, right? It's the same thing over and over again. But the fact that you can do one extra step and that you can balance these in alkaline media allows you to get a few extra points on the exam. All right. Like so. Right. So this one's balanced. Done. Okay, let's have a little look at this one here then. On the left-hand side, like so. All right then. So this is my reduction. And I just set it up like this. It keeps you straight in my head, all right? So let's see, this is the weird one. I've got O2, going to H2O. So I'm gonna have to, well, this is obviously gonna be 0 with my neon pink. Get oxygen in the neon pink. Elemental state, oxygen gases, is going to be 0, and this is going to be -2. Okay, all right, so therefore, what I need to do is I need to put 2 here. So this balances out the oxygens, yes, and then I need to put the electrons in, and so oxygen is going from 0 down to -2, so it's gaining 2 electrons per oxygen, right? But there's 2 oxygens, therefore it would be 4 electrons. Yeah. So you said 4 electrons, and so it's going to be what? Oxygen like this, O2 and 4 electrons. All right. And I'll show you how to double check this one, because this is a weird one, right? Because you look at this one, you go, hold on. But up here on the screen, you've got O2 being 0 and oxygen being -2. Yes, oxygen is 0 in the elemental state. And then it loses 2 electrons, become oxide, because oxide is -2, isn't it? And so therefore, it's going to be if you've got 2 oxygens to balance them out, it's going to be 4 electrons for this entire reaction. Let's see, atoms balance, oxidation state. So now what I need to do then is put the hydrogens in, and let's say I've got 4 hydrogens on the left-hand side, like so. Hold on, I've got to keep everything nice and organized here. I do love bit paper, it's just very nice, it really is. You know, all the digital papers, bit paper is nice. So we got this, right? Good. Now, scroll this up, do the usual, right? Same thing all the time, chemists. Look, you know, we're going to add them together. I always put the oxidation one at the top, right there. So I got 2Cr3 plus and 7H2O, because then I can see the electrons fall off the right-hand side. Cr2O7, 2 minus and 6 electrons. All right, plus 14H plus. Oh, this is going to be difficult one now, right? 6 electrons here, but when you got 4 electrons down here, so hold on. You have to multiply through by some common factor now. All right, H plus arrow goes to 2H2O. Okay, then. So on this one, then, obviously, where's my Syracuse orange here chemist? Look like this. I've got 4 electrons up here. I've got 6 electrons up there. What I'm thinking is I need a common factor that 6 and 4 both go into. I'm thinking 12. So I'm going to multiply this one by 2. And I'm going to multiply this one down the bottom by 3. Okay. I'm going to scroll my ink down like this. Okay. So yeah, we'll keep it in orange. Brighten things up a little bit. There you go, like this. Right. So on this one, I am just going to multiply through and then add together, right? So we don't get totally confused. All right. So what? I take this off. Hold on. Right. I got what? 4 chromium 3 plus and what? 14 H2O arrow. All right, 2 Cr2O7, 2 minus, and 12 electrons and 28 hydrogens like this. So multiply through by 3 on this bottom bit. So 3 oxygens like this. What, 12 electrons? Oh, good, the electrons canceled out. And 3 times 4 is 12 hydrogens like this, and that's going to go to 6 waters, right? So how I know that I got it correct on the exam, you know, you're doing the exams, I got a bit stressed. You go, look, 12 electrons on the right, cancel out with 12 electrons on the left. Good. All right. So now I'm just going to add them together, and then we can simplify down. There's a lot of simplification on this one, okay? So here we are on this one. All right, so get rid of my ruler option. Right, so I got what? 4 chromium 3 plus. It's supposed to be a plus. What happened? Like this. So I've got 4 chromium 3 plus like this, and 14 waters. And we will simplify down. Okay, and 3 oxygens like this, and 12 hydrogens like so. Yes, like this. So 4 chromiums, 14 waters, 3 oxygens, 12 hydrogens, arrow. All right, it's going to go to 2 Cr2O7, 2 minus, and 28 hydrogens. That's supposed to be a positive sign there, like so, and 6 waters, right? All right then. So before I change everything over to the alkaline, let's see if there's anything that I can simplify down on. And I'm thinking, yeah, straight off the bat, I can get rid of some waters, okay? So if I've got 6 on this side, and I've got 14 on this side, 8 is left on this side, and I got 12 hydrogens on this side, and that's going to cancel out with these, and that's going to leave me with what, 16? All right, mental math on the afternoon here. All right, so now let's see what we got, and then just convert over. All right, so got 4 chromium 3 plus like this, and 8 H2O, and whoops, 3 O2. All right, goes to 2 Cr2O7, 2 minus, and 16 H plus, like so. Hold on, 4 chromiums, 8 waters, 3 oxygens, 2 Cr2O7. Yes. Now, it's an alkaline solution, so I'm going to add the same number of hydroxide ions to both sides, right? Because obviously alkaline, you're going to have hydrogen ions floating around. So I'm going to add 16 OH minus on this side, and I'm going to add 16 OH minus on this side to make everything balance out. And so now, last time I'll do the ruler option like this. No, good enough. Like this, look. So, 4 Cr3 plus and 8, whoops, H2O and 3 O2 plus 16 OH minus, like so, arrow. All right, so on this side, I can convert this into water, right? So I've got 2 Cr2O7, 2 minus, and 16 waters, right? Like so. Okay, now cancel down wherever we can, which in this case, yeah, the 8 waters is gone and leaves you with 8 waters on this side. And you got this. So this is my final answer, like so. Right. So the reason why I did this one, chemists, is because, yeah, it's basically, well, to be honest, the most alien looking one that I could find. You know, I mean, not the run-of-the-mill one, is it? You know, you're thinking, first off, it's an alkaline, number 1. And then number 2, it just looks a little weird, like O2, H2O, and everything else. So hopefully, chemists, hopefully then what I've done here then in this bit is manage to explain how to balance redox reactions in acidic last week and alkaline media this week. All right, this is going to hold you in good stead for year 13, when you do fuel cells. So let's have a little look at a past paper question. All right, then. So here we go. Past paper question. We'll do this one live. All right. Because you know how I like to teach. I like to tell you, from a teacher point of view, all of the tripwires, as I call them, like things you got to watch out for. And they put this question on here for a reason. All right. So here we are. All right, then. So if I look at this one, give the oxidation state of nitrogen in the following species. All right. So here we are in, turn my pen on. Let me do some scratch over here. All right. So this is NO2 minus. All right. Yeah, obviously, this is -2 because it's an oxide, -2. It's not a peroxide, H2O2, but it would be -1. And so therefore, this would be +5. Right, so you're thinking, yeah, because +5, no, it wouldn't be +5, it'd be +3. Change it now. Why did I think +5? Hold on. Let's see. Yeah, no, hold on. 2 times 2 minus 4 is -2, and so, I got this one completely, I think, the wrong way there, right? This would be. What, +2? Why did I think it was +5? I don't know. Oh goodness. Like I said, chemists, I do these live. This is what, +2, right? So you're thinking, right, because 2, yeah, 2 times 2 minus 4. So 2 minus 4 is -2. So therefore, nitrogen would be +2. Now, I did look at the mark scheme for this one, chemist, and in fact, they got it here. They're a bit pedantic with the mark scheme, if I may say so, meaning that you have to put the plus sign in front of it. Hold on, that is NO2 minus. No, hold on a minute. I can't do mental math. What happened? I don't know. Maybe I need some more tea. All right, try it again. It's 3. Right, because this is, oh, I see. I was looking at this -2 up there. All right, hold on. Well, I do them live, chemists. I do them live, and so there we are. It's supposed to be -1. It's nitrite, NO2 -1. Yeah, so 3 minus 4 would be -1. Therefore, this would be +3. Now, chemists, you do need to include the positive sign. Right, I got the mark scheme, right? Include the positive sign. I know. You're thinking, well, hold on, isn't it implied if it's 3, isn't it implied +3? Yeah, you and I know that, but the examiner wants you to write down positive, so include the positive sign, first off, number 1. All right, and then for NO, I'll try to get it right this time. All right, not get confused with my oxidation state. NO, yeah, this is neutral, and so yeah, oxygen is -2, and so therefore this would be +2, right? So therefore nitrogen again would be +2 like this. All right, so my hint is please include, right, the positive sign. I know they're just being, a bit silly with the mark scheme, but it is what it is. All right, so here we are then down here. Write a half equation for the conversion of NO2 minus by nitrite in acidic solution into NO. Right, so chemists, look, what they've done is they basically, they're setting it up for you. Obviously the way that I teach is like, we do the easy questions and then we do the A-star questions, because this is where all the points are. On the exam, they've actually chunked it down for you step by step by step, which is nice. All right, so here we are. NO2 minus like so, and put this right in the middle right here, so I can doodle on like this, and O like this. Let's see. I've gone from a +3 down to a +2 oxidation state, so I need to add 1 electron on this side. And I can do that because the nitrogens, the element that changed oxidation state, is balanced already. So there's my electrons in. My next step was we have to put the waters in 2 oxygens on this side, 1 oxygen on this side. So I need to add a water in like so. Let's see, then I've got 2 hydrogens on this side. So what, 2 hydrogens like this on this side, and that one, yeah, it should be balanced. Yeah. All right. So again, we're doing good. All right. Half equation for the conversion of I minus, but it's right in the middle, so you can actually work on it, into I2. All right. So chemists, what I'm thinking is I got to balance the atoms. I got to put 2 iodines, 2 iodide like this. I2. Yeah, this is obviously -1. This is 0 oxidation state, but it's a change of 1 electron per atom, right? So it's like iodine, the I minus going to I would be I minus I would be losing 1 electron, wouldn't it? But iodine, I2 is diatomic, therefore we've got double the element, the atoms, and therefore this is going to be 2 electrons. And so I need to put this on to, this side here, like so. Now, do I need to worry about oxygens? No. Hydrogens? No. Yeah, I think I've got that right. All right, so hope so. Here we go. Overall ionic equation. Oh, well, this one's nice. Now, chemists, really quick then, all right. Obviously, I'm going to have to multiply with my Syracuse arch. Right, I have to multiply the top one here by 2. Why? Because I've got 2 electrons in the bottom on the right. I need 2 electrons on the top here. And so, I'll just do it in Syracuse arch right now. So would this be, hold on, 4H plus and 2 electrons and 2 NO2 like so. Arrow goes to 2 NO and squeeze it on there, 2H2O. And down here then, I got my 2 electrons, that's fine. So I was going to write down 2I minus like this. I'll try to keep the arrows lined up so we can see what's going on a little bit easier. Okay, so first thing is, yes, the electrons cancel out like so. So I got what, 4 hydrogens like this. Hold on, so I got 4 hydrogens like this, yeah. And 2 NO2 minus, 2 NO2 minus like this, and 2 iodides like so. Arrow, and on this side I'm going to have what, 2 NO and 2 H2O and I2. Right. So did I get that right? We double check real quick. Oh, yes, I did. Well, there you go. Good. All right, then. Now, can I solidify anything down? As in hydrogen ions? No. Waters? No. We're done. Good. Now, chemists, point of order then is this one. All right. Sometimes the mark scheme, they do like that you write down the equation of state. In other words, they don't. I talked about this last time, Kim. It's just like this. Look, it's like bandwidth. You've only got so much bandwidth, like so much stuff you can put into your head for exam day. And keeping track of whether you're supposed to write down the equation of state for one reaction here or a different reaction over here is just wasting bandwidth. So what I say is this. Well, at the end, after you balanced everything, at the end, write in the equation of state. And so therefore, I'm going to put in a little aqueous here. Yeah, and if they want it, great, you've got the mark. If they don't want it, don't worry about it. All right, iodine is going to precipitate out solid. By the way, water is a liquid. So yeah, I know that. We've put on aqueous. Well, the next thing is, what's it dissolved in? Yeah, itself. Okay, so anyway, chemistry joke there. I like that one. Anyway, state the role of NO2 minus in the reaction with I minus. Let's see. Well, I minus was oxidized. We know this because we've got electrons on the right-hand side. So I mass was oxidized and the NO2 was reduced. So because the NO2 was reduced, it's accepting electrons from the I-, which was oxidized. Therefore, right, to get that right, if the NO2 is accepting electrons on the left, it's going to be getting the electrons from the other half equation on the right, which means the half equation here was oxidized. And so therefore NO2- is an oxidizing agent. Oxidizing agent, as in, you know, it causes something else to be oxidized, right? Now, they do enjoy putting this type of question, chemists, onto the exam just to go, well, basically just mess with your mind, you know, oxidizing, reducing there. Just keep it straight, you know, one's oxidized, one's reduced, one's the oxidizing agent, one is the reducing agent. All right, so on this one, okay, I think we've got time. Look at my, yeah, we've got time just to go wrap up this one. Okay, and looks like next week we'll do some more of these. Or if you want me to do something else next week, chemist, by all means, drop me an email. You know, you've all got my email address, so just like drop me an email, and we'll do something else. Okay, so the aqueous solution, nitrite ions react with acidified dichlorate 5 according to the equation. Oh, very nice. All right, let's see, 25 cubic centimeters of sodium nitrite required this amount of potassium chloride. All right, so how I do it, chemist, is this one. And I guess we've all got ways of doing titration reactions, but how I do this, the very first thing I do is I just write everything down, and then I take the data and I write down below each species the information that they give me. And so therefore I don't get confused, which, you know, does happen. If you read the wrong oxidation state, for example, you can get confused on that pretty good. All right, so here we are then. Now let's see. So I'm going to do automatically. I just write down CNV, concentration moles volume. All right, CNV, concentration moles volume. Whether I need it or not, I just automatically write it down like this. Okay, let's say 25 cubic centimeters of sodium nitrite. So right here, this is 25 cubic centimeters like this, sodium nitrite required. All right, this is what, 27.4 cubic centimeters. Let's see, this is what, 0.02. Hold on, can I write 0.02 a little bit better? I think I can. 0.02 mole right there, moles per decimeter cubed. Right. And what they wanted to know is concentration in grams. Oh, good one. Yeah, sure. The shortcut. We're doing this one now. It's real easy. All right. Of sodium nitrate in the sample. Okay, then. So, what I'm going to do is change pen colors to orange. All right. And I'm going to scroll my board up a little bit like so. So you can see what's going on. All right. Very first thing I did is I looked at this and I said, right, I got 2 out of 3 variables on this one. And so I can solve for moles of my chlorate right here. And then I can go over the molar bridge, which is 2 to 5. And I can get moles of my nitrite. Then I can get my concentration and I can convert it over. Right, so here we are then. And I'll keep this in orange. So chemists, by the way, all right, do me a favor, this one. You've always got to write down what you're talking about for the examiner, as in label it. So moles of ClO3 minus, because All right. You know, if your teacher's marking the paper, or if the examiner's marking the paper, like next year. I mean, obviously, when I recorded this live stream, it was the ALs were cancelled, but you're thinking next year they could be back on. All right, then here we are then. So label it, because it's going to be scanned and then just sent up to somebody to look at a computer screen and mark it, right? So here we are then. I need moles of this. And so you know the concentration is moles of a volume. And so moles is going to be concentration times volume over 1,000, like so. Right, and so moles then is going to be 0.02 times what, 27.40, all right, over 1,000, because I got to convert back into decimeters cubed. All right then, and so if I did look at this one's what, 5.48 times 10 to the minus 4, right, moles of ClO3 minus, right? Now, if I come back down to here, right, MS down to here, I am out to a minimum, see 25.0, I'm out to a minimum of 3 significant figures, right? So as I teach it, you round off at the end, not in the middle, otherwise you get what's known as round off error, okay? Rather painful because it costs you points. So now then, all I've got to do is it's got to get moles of my nitrite. So moles in Syracuse orange of nitrite, NO2 minus, like so, is going to be, concentration is, no, hold on, don't concentration, hold on. It's the ratio. Right, it's going to be, what, 5.48 times 10 to the minus 4. And again, chemists, I'm old school. All right, I just write it down so that I can follow along and the examiner can follow along, you know, because I can tell you, well, from a teacher point of view, I mean, it's like, sometimes you know, you're just not going to follow arrows and scribbles on the page and trying to figure out what it is. If you can't figure out what it is, well, you know, right, so 2 to 5, right? So I need 5 moles of NO2 minus over 2 moles of ClO3 minus, like so. And so let's see, what did I get? I did this before. I got what, 1.37 times 10 to the minus 3 moles of NO2 minus. Now, obviously, looking at this one, chemist, you know, you know, all right, look at this equation here, right? The sodium ion and the potassium ion, the reason why they aren't in the equation is that they're spectator ions, you know, so they just cancel out. Now then, I've got moles of NO2, and so all we need to do now is we just need to get the concentration. So I've got the concentration of my NO2. Right, is now on this one, they did give it to you as ding ding ding. Oh, it was in 25 cubic centimeters, right? All right, so concentration of NO2 minus is what, moles of a volume over 1,000. There's got to be decimeters cubed on here, chemists. So what, 1.37 to the negative 3. And it's what, 25 over 1,000. Got to convert this over. All right, which is going to be, right, 0.0548 moles per decimeter cube, right? Now, this, yeah, this is the standard way of doing a concentration. However, oh, the examiner was in a bit of a mood when he wrote this question because he wants to know, do you know what the trick is to go from moles per decimeter cubed to grams per decimeter cubed? And the answer is yes. You just multiply by the molar mass. All right, so let's see, you got 0.0548 moles per decimeter cube, like so. And the molar mass, I'll put up here, the molar mass of sodium nitrate, NaNO3, no, it's not, that's NO3 should be, of, all right, let's see, 16 times 3 is 48. And 48 and 14, yeah, so anyways, what, it's got to be, we want the actual concentration at the end, it's got to be sodium nitrate. Sodium nitrate is going to be what, 69 grams per mole. So I'll do 69 grams per mole, like so. And you end up getting the concentration of sodium nitrate in grams is going to be 3.78 grams per decimeter cubed, right? Like so. Right then. So, yeah, this one is a typical redox equation type question. Now, what I've done, chemists, is this one. Yeah, there's a few that you always just need to know. I mean, like what they're getting at is, and we'll do these next time, right? Is that you take the 2½ equations and then you combine them together, and then you do some kind of a titration. Like I think in year 13, it's the permanganate ion, all right, that they do. And so there's a couple of classics that they do, but it's always going to be, you have to write this equation here, and then you end up with a calculation which says, can you do the ratio 2:5 or 1:6? All right, I think that the one next time, I'll do the one with iron next time. I think it's like chromium and iron. One gets oxidized, one gets reduced down, and it's like a 1:6 ratio. So what I'm thinking is, chemists, is that hopefully that kept you going this week. All right. Next week, what we'll do is let's have one more lesson on redox reactions, and I'll look at some examples. So I'll look at the one that they'll put on the paper in year 12, which is going to be the extraction of metal ores. Okay, so we'll do that one next week. And I think let's do a redox titration for the year 13s as well. Okay, so having said that, chemists, let's call it a wrap. All right, Alistair, hope you enjoyed that one. Hope you found it beneficial. All right, everybody have a great day if you catch me on the YouTube, and I will see you next week. So everybody take care.